Welcome back to part 2 of section 4.9. All right, so in this section we're going to take a look at something called the particular solutions with initial conditions. So what we're going to take a look at in this section is how an initial condition, or how knowing something about the original function or a point on the original function, can help us take a particular solution and turn it into an exact solution. Right? So some language to begin with. If you are given an equation that involves derivatives of a function, that equation is called a differential equation. Now they have first degree differential equations, second degree differential equations, third degree differential equations. The degree of the differential equation tells you what type of derivative is in it. If your equation just has a first derivative in it, then it is called a first order or a first degree differential equation. A second order or a second degree would have a second derivative in it. Now, if it has a second, it might have a first also, or it just might have a second, but second's going to have a second, third would have a third, and so on and so forth. All right? So, for example, if I were to ask you to find me the antiderivative equation, that is, if I were to ask you to find me big F of this first order differential equation, dy dx is equal to 3x squared minus 1, you would tell me that the antiderivative, or the general solution, is x cubed, and that came from the 3x squared, minus x plus c. And the reason we put the plus c on, just to remind you, is because there could have been some constant value remember that's a number like a 5 or a 7, that could have been sitting there, and when you took the derivative would disappear, and we'd have no evidence of its existence, and because we'd have no evidence of its existence, we have to put in the c to say, hey, there could have been. But what if you were given an initial condition that original function passed through the point 2, 4? Now remember, whenever you're given a point, an x, y, that actually also could be thought of as an x comma f of x, a point that is, for this one, 2 comma f of 2, or more importantly, we could say that we have an initial condition that tells me that f of 2 is equal to 4. And what that will allow us to do is it'll allow us to solve for the value c for this initial condition problem. Or we can say then that 2 cubed minus 2 plus c must be equal to 4. Okay, where did this come from? I took the function f of x equals x cubed minus x plus c, plugged in the 2, and I'm going to grind out an answer now. So 2 cubed gives me 8. 8 minus 2 is 6. So I got 6 plus c is equal to 4, and that tells me then that c must be negative 2. And if I put it all together, wrap it up, make it look pretty, I say that the particular solution to this initial condition problem is f of x is equal to x cubed minus x minus 2. And this is a function whose derivative is 3x squared minus 1 and passes through, or has the initial condition, f of 2 is equal to 4. Now, if you think back to your college algebra, back in college algebra, you were taught that this value on the end here, this constant that is either added or subtracted, represents a vertical translation. Right? So by changing that value on the end, we're taking the rest of it, the algebra of that function, and just vertically translating it up and vertically translating it down. And when you slide that function up or slide it down, we're not changing tangent line slopes. So effectively, we're not changing the derivative, we're just changing its location on a graph. Right? And so what we've done here is we've solved a first order initial condition differential equation problem. They can get harder. They could look like this. What does this tell me? Well, it tells me to find a function f if the first derivative is that mess and it has an initial condition f of 0 is negative 2. Right. Well, let's think of this in terms of steps. Right? What would step 1 be? Well, step 1 would be to turn f prime into a general solution or a general antiderivative, and then step 2 would be solve for c, which would give us the particular solution. So that's what I'm going to do here. First thing I'm going to do is I'm going to copy down that f prime, but I'm going to rewrite it a little bit so it becomes incredibly obvious what we're doing here. So when I write it like that, I'm writing it like that so we can see the antiderivatives. My first term that I have to take the antiderivative of is e to the x. And I know that the antiderivative of e to the x is just e to the x. The second term that I have to take the antiderivative of is this 20 times the quantity 1 divided by 1 plus x squared. So that's going to be 20 times arctangent of x. And of course, since we find the general solution in that first step, we're going to put that plus c on the end. Now I need to turn the general solution into the particular solution for the initial condition f of 0 is equal to negative 2, which tells me that when x is 0, the entire function needs to be equal to negative 2. Now I just realized something. I made a small mistake, and I'm going to correct it. This should not be capital F. Since I was given f prime, what should that really be? That should be our lowercase f, so I'm going to go back and correct that. And now I'm going to solve for the initial condition. The initial condition tells me that negative 2 is equal to e to the 0 plus 20 times the arctangent of 0 plus c. Okay, I'm going to do a little bit of simplification. Negative 2, e to the 0 is 1, plus 20 times, what's the arctangent of 0? Well, the arctangent of 0 is 0, plus c. So it looks like we've got negative 2 is equal to 1 plus c. So c must be our negative 3. Okay? And then I'm going to wrap it up and make it look pretty, because solving for c here is part of the process, but it is not the final solution. So I'm going to grab this, I'm going to grab this, I'm going to put them together and say that the final solution is that the function f of x would be e to the x plus 20 arctangent of x minus 3. And there is my particular solution to the first order differential equation problem that we were just given. Okay? Finding an antiderivative, solving the general solution for a particular solution. Okay? All right, let's take a look at this one. More challenging, because what are we given? We're given a second order differential equation. We are told that f of x is f prime isn't known. We are just given, so we are given f double prime, the second derivative. So to get back to f, we're going to have to take an antiderivative and then a second antiderivative. All right, so let's get started. If f double prime is this, then f prime will be the antiderivative of that. So antiderivative of 12x squared is going to be 12 times x cubed divided by 3 plus 6 times x squared divided by 2 minus 4x plus c. Okay? Now, I can't actually solve for that c because the initial condition information that they gave me all deals with f of 0 equal to 4, or f of 1 is equal to 1, and I've got f prime. So I'm going to have to take another antiderivative, and then I'm going to have to figure out what to do with that when I take the antiderivative. Right. So before I worry about taking the antiderivative, I'm just going to go through and rewrite this and clean it up a little bit. The 12 divided by 3 here is going to give me 4x cubed. The 6 divided by 2 here is going to give me a 3x squared minus 4x plus c. And then when I take a second antiderivative, f prime is going to turn back into f. That's going to give me x to the 4th plus x cubed minus 2x squared plus c times x. Now right there, c is a constant, like a 9 or a 7 or a negative 3. And the antiderivative constant is a constant times x. And now I'll be tempted to do this, but I can't. Because if I write plus c on the end, then what I'm saying is, I am saying that that and that are the same number. And they don't have to be the same number. So one way to deal with it is to call this one's like C1, to call the first one C sub 1 and the second one C sub 2. Another way to deal with it is, rather than using 1s and 2s, would be to call that one C and this one D. It really depends on the author of the textbook and how they decide to do it. Right? Both of them are acceptable. I believe Stewart uses C's and D's, so that's what I'll go with here. Right? So now what I need to do, though, is since I have a function f of x, and I have initial conditions about f of x, I need to solve for C and D. Right? Now, me being the lazy man that I am, I recognize something right away. This f of 0 is very convenient, so I'm going to use that first. F of 0 is equal to 4 tells me that 4 is equal to 0 to the 4th plus 0 cubed minus 2 times 0 squared plus c times 0 plus d, or that d is equal to 4. I like that. And now I'll use the other initial condition to get me that, let's see, 1 is equal to 1 to the 4th plus 1 cubed minus 2 times 1 squared minus 4 times 1. Wait. Minus 2 times 1 squared plus c times 1 plus 4. I got my c and my d mixed up there for a second. Okay? So I took the purple equation here, and I plugged in 1 for all the x's and set the whole thing equal to 1. Let's see what we got going on here. If I clean that up a little bit, I've got 1 is equal to 1 plus 1 minus 2 plus c plus 4. That all cancels. Negative 3 is equal to c. Final step, wrap it all up, make it look pretty, write it as a function. I get that f of x is equal to x to the 4th plus x cubed minus 2x squared minus 3x plus 4. We solved for the c and the d there to make that thing work. And these are applications of antiderivatives, finding a particular solution with an initial value, or in this case 2 initial values, for a differential equation. Right? And then what we could use this for in application is going back to our favorite process, that is a particle in motion. And we have position functions, and we have velocity functions. And then we know from what we've gotten so far out of calculus is that if I take the derivative of position, I get velocity. So that means that the position function is the antiderivative of velocity. And I know that if I take the derivative of velocity, I get acceleration. So that means that the acceleration function can be related to velocity by taking an antiderivative. Right? And so if we knew some initial values for acceleration and or velocity, we could find position functions. Right? So this is just what we just got done doing, taking an antiderivative and solving for the general solution, but with an application wrapped around it. Right? So for example, a particle moves in a straight line with an acceleration given by the function a of t equals 6t plus 4. Its initial velocity, remember, whenever you see the initial with something, that means that the time is 0. And its initial displacement, initial time is 0. So its initial velocity was negative 6 centimeters per second. So moving left at 6 centimeters per second. And its initial position was s of 0 equals 9. Find the position function. So essentially, this is the problem we just did. This would be representing our f double prime, and we're asked to find f. Just now we've given it fancy names of A and S, right? So if I think back, if I remember correctly, the process was antiderivative. I think I can do that. So if A of t is equal to 6t plus 4, what would V of t look like? Well, I take the antiderivative of that. It's going to be 6 times t squared over 2. I'll take the antiderivative of 4. That's going to give me 4t plus some unknown constant. Now, if possible, I'm going to solve for c at this point. Right? So I know that v of t is equal to 3t squared plus 4t plus c, and then I'm going to use this because I can to solve for c. I couldn't solve for c on the first step in the last problem because I didn't have a derivative information. But now I do. I have v sub 0. I have negative 6 is equal to 3 times 0 squared plus 4 times 0 plus c, or that c is equal to -6. And if I wrap that up and make it look pretty, that tells me that v of t is equal to 3t squared plus 4t minus 6. Right? Now I need to work backwards one more step to get from velocity back to position. So if this is my velocity equation, what will position look like? What will s of t look like? Well, the antiderivative of 3t squared is going to be 3 times t cubed over 3 plus 4 times t squared over 4 minus 6t plus, and I'm going to call it d. Even though c is gone, I don't want to have two c's floating around in my same problem that represent different quantities. So I'm going to go with d here. Okay? Now I'm going to use the initial condition that s of 0 is equal to 9. 9 then is equal to, well, those cancel, so 0 cubed. That should be a 2 there. Sorry about that. T squared over 2. Plus 2 times 0 squared minus 6 times 0 plus d. So 9 equals d. And then I'll wrap it all up, make it look pretty. And what do we have here? We have that the position function s of t is equal to t cubed plus 2t squared minus 6t plus 9. So essentially we have solved a second order differential equation problem, but we didn't call it that because we were talking about solving a rectilinear motion problem. Rectilinear motion. Okay. Last problem. A ball is thrown upwards with a speed of 64 feet per second from the edge of a cliff 80 feet above the ground. Find the height above the ground t seconds later. When does it reach its maximum height? When does it hit the ground? Okay, so this problem's a little bit trickier just simply because I have to try to figure out what all this means. So first off, a ball is thrown upward with a speed of 64 feet per second. That tells me that v sub 0 is equal to 64. Right. From the edge of a cliff, 80 feet above the ground, that tells me that s sub 0 is 80. Now I'm making some implications here when I make those two statements. First off, I am saying that this is height 0. So then here is 80 feet. I'm also saying that this direction is positive velocity and that that direction is negative velocity. Okay? All right, so I need to figure this. Wait a second. This looks a lot like the last problem. The only difference is in the last problem I was given a acceleration function to start with. Here we're not given that. So I guess you're just supposed to know it. I guess you're supposed to know that a of t is either equal to negative 9.8t or negative 32t. Negative 9.8 would be meters per second. I'm sorry, negative 9.8 or negative 32, no t's. Because a of t would be the acceleration, which is a constant due to gravity, and negative 9.8 would be what you would use if your units were in the metric system, and negative 32 would be what your acceleration for gravity would be if you're using freedom units like we use here in America, our freedom units. Okay. So since this problem is written in feet and feet per second and all that, then I'm going to use my negative 32 here. And so I get that a of t is equal to negative 32, which means that v of t must be equal to negative 32t plus c. So then I can use my initial condition over here to solve for c. And that's going to give me, what is that going to give me? What is that? That's going to give me that 64 is equal to negative 32 times 0 plus c, which means that c is equal to 64. So then I've got v of t is equal to negative 32t plus 64 right? And then from there, I can go back to s by taking another antiderivative. So s of t is equal to negative 16t squared plus 64t plus d. I'll use the initial condition about height to solve for s of t. That's then going to give me that 80. Oops. Wait, let me get rid of those stupid arrows. 80 is equal to negative 16 times 0 squared plus 64 times 0 plus d, which means that d equals 80. So then wrapping it all up, making it look pretty, cramming in at the bottom of the screen here, I get that s of t, my position function, is equal to negative 16 t squared plus 64 t plus 80. Okay? So I have found its height above the ground t seconds later. Okay? And now I just need to answer the next two questions. Now I'm out of space here, so let me add in a page. Let's see, page manipulation, insert a page, insert it after, insert one page. There we go. Okay, and so now I'm supposed to find out when does it reach its maximum height and when does it hit the ground. So if I redraw my picture down here, we're starting here. What is it, a ball? A ball. The ball goes up, the ball goes down. At every point in time, the height of the ball, s of t, can be found by negative 16t squared plus 64t plus 80. Right here is going to be maximum height. Right here is going to be when the ball hits the ground. My job is to find those two things. Well, finding the max height tells me to find the maximum of that function. Well, I could use calculus, but you guys know I'm lazy. Isn't that a parabola that opens down? And the parabola that opens down, the max is at the vertex. And the vertex of a parabola is negative b divided by 2a comma f of, or in this case it'll be s of, negative b divided by 2a, which, if you really want to know, this formula that I just wrote there comes from calculus. That's where it was developed. We just stuck it into college algebra and said, here's the result of calculus. But we don't tell you that. Right? So for this problem, what's b? Well, b is 64. And what's a? Negative 16. So then plugging things in, negative b divided by 2a is going to be 64, negative 64, sorry, divided by negative 32, which is 2. So then the vertex is when t equals 2. So I'm going to go back up here for a second. When does it reach maximum height? I'm done. Time equals 2. So max height is at time 2 seconds. What is the max height? I really don't care. They didn't ask me to find that. But if I needed to, could I just take this 2, put it into the equation, and get the max height? Now, the trickier one is going to be, when does it hit the ground? How do I find out when it hits the ground? Again, I'm solving for t, because I don't know when it hits the ground, right? When, time. So when does it hit the ground? Well, what's the height when it hits the ground? Right? Well, the height would be 0. So hitting the ground means that s of t equal to 0 and solve. So I'm going to say 0 is equal to negative 16 t squared plus 64t plus 80. Okay? 0 is equal to negative 16 times the quantity t squared minus, what is that, 4? T plus 5. negative 16 times t, what is that going to be, minus 5 times t plus 1, I believe. Let's see, that's going to be negative 5, negative, yeah. So then we get that t is either equal to 5 or t is equal to negative 1. Now, this solution doesn't make any sense because although in some problems going back in time makes sense, but this problem it doesn't, because back in time the object wasn't moving according to this model, because at time 0 is when we threw it up in the air. So then the only thing that makes sense is this, and so we would say that the ball hits the ground after 5 seconds. And there we go. This brings us to the end of Chapter 4, Section 9. You should be able to complete the 4.9 homework now. And I'll see you all back here for 5.1.